All right. Good afternoon, class. I'm trying a bit of a different format today, simply because the broadcasting software was really laggy yesterday, and so I'm just trying with just the single window today. So we'll see if it works. Hey Ava, hey Rourke. So please give me feedback and let me know if it's working better than what I was doing before. So we've got kind of a tough lesson today, I'll be honest with you. So we're going to learn what are called Kirchhoff's laws. And so the first of Kirchhoff's laws is called Kirchhoff's, hey Ricky, Kirchhoff's current law. Okay. And what Kirchhoff's current law says is that the sum of the currents flowing into a junction is equal to the sum of the currents flowing out of the junction. Okay? When I say a junction, I just mean wires joined together. So let's suppose I have a bunch of wires joined together, maybe 5 of them. Okay? And this wire and this wire are carrying current into the junction. And this wire are carrying current out of the junction. So let's say that this is 7 amps, this is 12 amps, this is 9 amps, and this is 1 amp. And we want to figure out what is this unknown current. So what we want to do is we want to know how much current is going in to this junction. I've got 7 amps going in and I've got 12 amps going in. So that's 19 amps going in. Okay. And then if I look at the current going out, there's 9 amps going out and 1 amp going out. That's a total of 10 amps going out. So we can see that the amount, at least with just these 2 wires, the amount of current going out of the junction is less than the amount that's coming in. So I can conclude that this unknown, current would have to be going, the unknown current is 9 amps. So this is 9 amps going out to satisfy Kirchhoff's current law. Okay? So that is Kirchhoff's current. Then there is also Kirchhoff's voltage law. Kirchhoff's voltage law says that the sum of the voltage changes around any loop in the circuit has to be equal to 0. All right. So a good example of that is if we have, like, for example, a voltage divider circuit. So we got a voltage divider circuit, and let's say this is 12 volts. And then we have these resistors. Maybe this is a 6 ohm resistor. This is a 3 ohm resistor. Okay. Then if you were to solve this voltage divider circuit, you would find that there's a drop of 8 volts across this one, and there's a drop of 4 volts across this one. Okay. So Kirchhoff's voltage law says that, well, if we were to go around this loop in the circuit, there is a 12 volt rise, followed by an 8 volt drop, followed by a 4 volt drop, and then we come back to where we started, and that equals 0. So we have 12 minus 8 minus 4 equals 0. So you might remember when I was talking about voltage dividers, I said that the reason it's called a voltage divider is because the voltages that each resistor gets, they add up to the battery voltage. Well, that is a reflection of Kirchhoff's voltage law. All right. Okay. So we're going to use this. It turns out that Kirchhoff's voltage law and Kirchhoff's current law, so I call them KCL and KVL, can be used to solve any circuit. So basically, these laws are the main circuit analysis tools that electrical engineers use, okay? And we go into it with a little bit of depth this year. And if you take my AP Physics C class, we go into a lot more depth, okay? So let me show you how you can apply that to really complicated circuits, okay? So let's suppose I have a circuit with multiple batteries. So let me just draw a circuit here. So maybe it's, maybe it looks like this. Like so. Maybe this is a 6-volt battery. This maybe is a 9-volt battery. This is a 4-ohm resistor. This is a 5-ohm resistor, and this is a 2-ohm resistor, for example. Okay. So what we want to do is we want to first of all label the currents. So how many distinct currents are there in this circuit? Well, if we think about it, there are actually 3 distinct currents in this circuit. So one of the currents is the current that flows along here. Now, why do I say that that's one current? Because you can see that on the road from here to here, there's no branches where current can go out the side or anything like that, okay? So this is going to be the same current everywhere along this piece of wire, okay? Anytime the wire breaks as well, and then this is going to be a new current. So there are 3 distinct I2 and I3, okay? And I'm just going to randomly pick directions. I'm just going to guess what is the direction that the current will flow. It does not matter if you guess wrong. You just have to guess a direction for which way does the current flow. So I'm going to guess that this current is flowing in that sense. So it's going around like this. So I1 is swinging around like that. I'm going to guess that I2 or I3 over here, and that I2 is going down like that. So basically what I'm assuming is that the currents are going like this. Okay? So these currents are kind of coming together and joining and making that current. Again, I cannot stress enough. It does not matter if your guess is wrong. Okay? The next thing we have to do is we have to label the positive side and the negative side of each thing in the circuit. Now, batteries are easy. Batteries, I told you that the longer line is the positive terminal of the battery. Okay. So this would be the positive terminal of the 6-volt battery, and this would be the minus terminal. this would be the positive terminal of the 9-volt battery, and this would be the negative terminal. Okay, so labeling the batteries is pretty easy. Labeling the resistors is a little bit trickier. So let's suppose I have a resistor, and let's suppose that I guessed that the current is going through it from left to right. Okay. The upstream side of the resistor is going to be the positive side of the resistor. So this is positive side. See how that's the upstream side, and it goes to the downstream side. So positive and negative. So based on that, I can see that this current is going to the left. So the positive upstream side would be this, the negative side would be that. Okay. Here the current is going down. So the positive side would be the top and the negative side would be the bottom. And here I can see the current is going from right to left based on this arrow. So the upstream side would be the right side and the downstream side would be the left side. Okay. So now what I'm going to do is I'm going to write a Kirchhoff's current law equation for a junction. Theo asks the question, so it's purely based on the direction that you guessed the current flowed? Yes, it is 100% purely based on which way you guess the current flows. And it actually, yeah, so you just guess it and you label the positive side based on your guess. So we're going to write Kirchhoff's current law for a junction. I'm going to pick this junction. You could choose either one. I'm going to pick the top one. So Kirchhoff's current law, and it's based purely on my guesses for the direction of the current. I can see that I1 is going into the junction. I3 is also going into the junction. I2 is going out of the junction. So the currents flowing in are I1 and I3, and the current flowing out is I2. So that's Kirchhoff's current law. Okay. Why did it not matter? Oh, Andrew asked a question, can one wire have current flowing in both directions? No, it can't. And the reason is that we've just labeled each segment of wire with one distinct current. So then you can see that the current flowing into the junction is I2 and the current going out is I1 and I3. So if I had used the bottom junction, I would have had I2 equals I1 plus I3. It's the same equation. So it doesn't matter which junction you choose. So that's the left loop. So when I say the left loop, I mean this loop right here. Okay, so I'm going to go around this loop clockwise. It doesn't matter where you start. So I'm going to start going around. It also doesn't matter which way you go around the loop. You could go whoop or does not matter. Okay. Actually, I'll start here. What the heck? And when I write Kirchhoff's voltage law, you have to remember the voltage drop across a resistor is given by Ohm's law, V equals IR. Okay, so I'm starting right here and I'm going around the loop like this. So the voltage change across the battery is 6 volts. Is it a rise or a drop? Well, I went from negative to positive, so that is a rise of 6 volts. Okay, so I have plus 6. Then I go around the loop and I get to this 5 ohm resistor. And you can see that based on the sense of my loop, I'm going down through this resistor. So I'm going from the positive side to the negative side. So that is a drop. It's a resistor, so the drop is I times R. What is the current value that this resistor experiences, it's called I2. And the value of the resistance is 5 ohms. So I have I times 5. And then I get to this corner and I continue going around my loop to right here. And so when I hit this 2 ohm resistor, notice how I'm going from positive to negative through that resistor. So that's a drop. Okay. The current that resistor experiences is I1. See how it's on the I1 segment? That's the road it's. So that says, so what I've done is I've added up all the voltage changes around the loop and I set it equal to 0. So that's my KVL equation for the left loop. Okay. Now, step 5, I'm going to write a KVL equation for the right loop. Okay, I'm going to write a KVL equation for the right loop. So now what I'm going to do is I'm going to go around this right loop in the counterclockwise sense. I'm going to go ahead and start right here. So if I go up along this segment of the loop, you can see I go from, I pass through this resistor, so I have to add up that voltage drop. See how I go from negative to positive? So that's a rise of, and it's a resistor, so the voltage rise is I times R. So I have a current, which is I2 along this segment, and a resistance, which is 5 ohms. So that's the first term. Then I get to the top of this segment, and then I turn right and go along this segment. And you can see I run into this 3. So I have plus I3 times R, which is 4 to negative. So that's a drop. And batteries have just a defined drop independent of the current. So it's just 9 volts. So I have minus 9. And after I go through the battery, I get back to my starting point. So I set it equal to 0. Okay. If you had a more complicated equation or a more complicated circuit, maybe with an additional loop or something like that, then you would basically have more KVL equations for each loop. And you would have also more KCL equations because you'd have more junctions, okay? But for this simple circuit, that's all you have. And you'll notice that basically I have 3 unknowns. I1, I2, and I3. And then we also have 3 equations. So we can solve the 3 unknowns, or the 3 equations for the 3 unknowns, and we can figure out what all the currents are, okay? So that is how you use Kirchhoff's laws to solve complicated circuits. I'm not going to expect you to solve the system of equations. All I'm going to expect you to do is write the system of equations, okay? So thank you very much. I hope that made sense. Thanks for your questions. And give me some feedback in the live chat if this was smoother than the other broadcast method that I've been using. All right. Thank you very much and have a nice day.